This topic is empirical model development, and you may know that the word empirical in English means based on experiment or observation rather than theory. So up until this point in the course, we have used basic engineering principles to construct dynamic models of the process, and then using our dynamic models for a given input, we could predict what the output was going to be. In many cases of practical interest, however, the process itself is so complicated, or too many properties of the process are unknown, to construct a dynamic model using theory, or using first principles. In this situation, we may wish to develop a dynamic model by subjecting the process to a known input, measuring the output, the change in the output variables with time after a known input, and then developing a model that fits or describes the data. And this is called empirical model development because we do not attempt to understand the process from first principles or based on engineering concepts like thermodynamics or material or energy balance. Instead, we collect data like an experiment. We perform an experiment on the process while it's operating. We make a change in the input. We measure how the output changes. And then we develop a model that describes the relationship mathematically. That's called empirical model development. Okay, so how is this going to work? The simplest case is where the process is initially at some steady state. At time zero, we make a step change in an input of magnitude m. We measure the response of the output variable, and the output variable changes with time approximately like this. Okay, this curve is exactly the response of a first-order transfer function, and so if we are lucky, our process can be described by a first-order transfer function. In that case, we only need to determine two parameters in our model, the steady-state gain k and the time constant tau. The steady-state gain can be found by looking at the long-time response. After a long time, the process approaches a new steady state with a final value equal to k times m. Since we know m, the magnitude of the step change in the input that we made, we can determine the steady state gain k from the final value. There are two ways of determining the time constant tau. This is the expression for the response of a first-order process in the time domain. There are two ways of determining the time constant tau. One is to look for the 63.2% response time. The 63.2% response time is the time constant tau. The second way is to draw a tangent to this curve at time zero, extend that tangent line up to the final value, and then go down to find tau. Okay, if our process is a first-order process, then empirical model development is not too difficult. Unfortunately, in reality, very few processes are truly first-order. A commonly used model that can approximately represent the dynamics of many realistic processes is the first-order plus time delay model. Okay, the first-order plus time delay, as the name suggests, is a first-order process, k over tau s plus 1, with also some time delay, theta. Now, our empirical model has three parameters, k, tau, and theta, and these need to be determined from experimental data, like a step response curve. Okay, so here is a hypothetical step response curve. We imagine the process was initially at steady state. At time zero, we made a step change of magnitude m in the input. We measured the output, and the output changed like this. Increased slowly at first, then faster, 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 finally slowed down and approached some final value, km, at long times. And we want to approximately describe this curve with a first order plus time delay model. The first order plus time delay model is going to have some amount of time delay theta, and then after time theta it's going to respond like a first order process. So it won't describe this part of the curve very well, but hopefully it will approximately describe the overall response of the process. So again, there are three parameters to determine: k, tau, and theta. As for the first order process, we can determine the steady state gain by looking at the long time response. The final value here will be k times m. Since we know m, we can determine k, the steady state gain of the process. Then, to determine tau and theta, it's suggested that we look at this curve and locate the inflection point. The inflection point is the point where the second derivative is equal to 0. That means the slope changes from increasing to decreasing. Over here in this part of the curve, you can see the slope is clearly increasing. Over here in this part of the curve, you can see that the slope is clearly decreasing. There must be a point on the curve somewhere between here and here where the rate of change of the slope is 0. And that's indicated here. That's the inflection point. The second derivative, the rate of change of the slope, is equal to 0. We identify the inflection point. We draw a straight line through the inflection point, tangent to the step response curve at the inflection point. And we extend that tangent line down here to the x-axis and up here to our final steady state value. Then we take this distance here as theta and this distance here as tau. Okay, the first order plus time delay model is adequate for many purposes, but sometimes we want a more complicated and therefore more accurate model. The most complicated model that's commonly used is the second order or second order plus time delay model. This is a second order process. Here there are three unknown parameters, k, tau1, and tau2. And the second order plus time delay model here has four unknown parameters: k, theta, tau, and zeta, or k, theta, tau1, and tau2. You can get an idea of the difference between a first order plus time delay model and a second order plus time delay model by looking at this diagram, which shows the response of this second order process for different values of the ratio of tau2 over tau1. We'll assume without loss of generality that tau1 is greater than tau2, and so this ratio takes on values between 0 and 1. When this ratio is 0, that means tau2 is 0, and we have the response of a first order process like this. As this ratio increases towards 1, we have a more pronounced inflection. The response is slower at first, then speeds up, speeds up, speeds up, and approaches the steady state value more quickly. This ratio being equal to 1 corresponds to the case where tau2 and tau1 are equal. Okay, so suppose we want to fit our step response data to an empirical model of this form: second order plus time delay. There's four parameters we need to determine: k, theta, tau, and zeta. This clever fellow Smith suggested a graphical method for determining the parameters in this model. To use the method, we first identify any apparent time delay, theta, and we eliminate that from the dynamic response. So we look at the graph, we see how much time delay we think is present, and then we remove that time delay. We shift the response curve to the left by an amount of time equal to that time delay. Then, after shifting the curve to eliminate the time delay, we find the 20% response time, t20, and the 60% response time, t60. We calculate t20 divided by t60, and then we find the values of t60 over tau and zeta from the graph on the next slide. Okay, here is the graph for using Smith's method. Here is a hypothetical step response curve. The times t20, the apparent time delay has already been removed. The times t20 and t60 are marked on the graph. Once you've identified t20 over t60, you can calculate t20 divided by t60, and then you can use these curves here to determine t60 over tau by going up to this curve and then over to the left. And you can determine the value of zeta by going up to this curve and then over to the right. Okay, as an example of using these methods, suppose a certain blending process is initially at steady state. At time 0, the flow rate of one stream in the blending process is changed abruptly from 20 liters per minute to 25 liters per minute. Concentration in the product stream is recorded as shown on the following slide, and you are asked to fit the data to a first order plus time delay and second order plus time delay model. And you're reminded to include correct units for all variables. Okay, the data are shown here. Take a moment and see if you can fit this data to a first order plus time delay and second order plus time delay model. Okay, assuming that you have attempted the problem, you might get slightly different answers depending on how you read the graph, but these answers are reasonable. Okay, a few remarks about empirical model development. In some cases, it may be undesirable to make a step change to the process input because this will cause a sustained disturbance to the process. In this case, we can use another input, such as a square pulse, but of course we'll need a different method, graphical or analytical, in order to determine our model parameters from the response of the output variable. Second point is that we can also obtain information about the process by subjecting the process to continuous oscillation. This method is called frequency response analysis, and it will be discussed later in the course. And finally, if we want to use an even more complicated process model, at some point we would stop using a graphical method and we would resort to using a computer to find the values of the model parameters that minimize the error between the model prediction and the actual process output. And the general term for this process is regression. Okay, to conclude our discussion of empirical model development, in some cases it may not be practical to develop a dynamic model of a process from first principles. In this case, we can construct an approximate dynamic model by subjecting the process to a known input and measuring the output. If a low-order model is adequate, like first order plus time delay or second order plus time delay, parameters can be determined graphically from the step response curve. If a more complicated model is necessary, it may be necessary to use regression to determine the model parameters or resort to a more sophisticated modeling method.